Hi. So again, we're continuing with the introduction to graphs. The idea here is that a person has seen many of the parts that we're going over. Maybe this person has seen this and this person has seen that, so it's not 100% overlap. But we're trying to fix vocabulary words and trying to make sure that everybody sort of comes at it from the same place, so we'll all end up in the same place. Okay, so next up is paths. We want to talk about how you work your way through a graph. So a path in a graph is a sequence of edges. And the node elements have to be arranged in such a way that they overlap. So the end of E naught has to be the beginning of E1. And the end of E1 has to be the beginning of E2, that sort of thing. So the end of E naught, n sub 0, 1, has to be the beginning of E1, n sub 1, 0. And that's what it says over here. It's harder to write down than it is to say. The path starts at node n00, ends at node nk1, and it has length k plus 1. Okay. Now, there's a lot of vocabulary words here. A person has to be careful not to get lost in the vocabulary, but some of it is necessary. So a path is a circuit or a closed path if the start and end node are the same, and the length is greater than 0. A path is simple if no edge appears twice. If the graph is directed, then in the paths, the node you have to follow an edge along the direction that the edge goes. You can't go down one-way streets. So if a graph is directed, the definition of path includes that direction. So again, the terminology is, in the first place, not completely standardized. It's actually getting better recently, but not completely standardized. Some authors have a very elaborate vocabulary of walks and trails, and you have to be a little careful. It can be the case that one person's walk is not quite what another person means by walk. But nonetheless, the basic idea of a path is you have to work your way through the graph. So here's an example of a path through a graph that we saw in the last video. So here I am at my house in Jericho, and I'm going Route 15 in Essex, and then down to Essex Junction to Five Corners, and then down to St. Michael's. So this is a path for me jogging from my home to St. Michael's. A graph is connected if between any two nodes, any two vertices, there's a path. And an example is that when you're surfing the net, when got your web browser up, and let's say you're looking at Google, then there's a path of network connections between me and Google. Somehow there's this you can trace a route between your computer and the computer that you're talking to on the internet. So that's a typical example of a path, and a graph is connected if you can get from any one to any other. If somebody reaches behind your computer and cuts the yellow wire, why you're no longer connected to the internet. The lemma is that in a connected undirected graph between any two nodes, there's a simple path. So you can eliminate the non-simple parts. You remember what simple path means? Simple path means that no edge appears twice. Okay, so the basic idea is that if you give me two nodes, there's got to be at least one path because the graph is connected. And now imagine that there's more than one path. From all the paths, even if there's only one path, from all the paths between the two, consider one that has the least length. So if there's a path of length 12 and a path of length 11 and a path of length 8, take the one of length 8. We claim that this path is simple. So if the path is not simple and some edge appears twice. Well, wait a minute now. So this part in here between the two e's, we could eliminate. Where it says ... e, we could eliminate that because there's an e, and we can hook the end of that e up to whatever the beginning of this ... is. So I could eliminate one of these ... e's. If you omit that from the path, then you get a shorter path. But that's not possible. We chose this to be the shortest possible path. So the shortest path is a simple path. A connected component, we saw that in the last video, connected component of an undirected graph is a subgraph in which any two vertices are connected to each other by a path. And I'll just have a simple example. I grabbed this tourist map of Nantucket Island off of the internet, and you can see some of the roads are included. Obviously not every road, but these are supposed to be bike paths. I guess some of the roads are included. Now, Nantucket Island is not connected to the mainland by a road, so it is its own component in the map of, for example, North America. In a connected component, though, any two vertices are connected to any other. Now, if you try to draw a map of Massachusetts and say any two vertices are connected to that, that's not right. Boston is not connected to Nantucket. But if you just restrict yourself to Nantucket, yes, indeed. So a connected component is where any two vertices are connected to each other by a path. Okay, we referred to these actually in the previous video too. Two particular kinds of path. An Euler path, it traverses every edge in a graph. A Hamiltonian path visits every vertex. And the theorem is that we talked about in the last video that a multigraph has an Euler path if all the nodes but two have even degree. And if there are two that don't have even degree, then one of them will be the start node and one of them will be the end node for the Euler path. If the path is a circuit, then every node has to have even degree because the start is the end by definition of circuit. We've already seen one direction, that if a graph has an Euler path, then all but two nodes have an even degree. And we're not going to prove the other direction. It's not actually all that difficult. You prove it by induction on the size of the graph. But it doesn't matter. The point is that it's an if and only if statement. Now, although Euler paths and Euler circuits, Euler path and Hamiltonian path may seem similar, deciding if an arbitrary graph has an Euler path is easy. We just did that. Deciding if an arbitrary graph has a Hamiltonian path is, as far as we know, very, very hard. So it's funny. Visits every edge is easy. Visits every vertex is very, very hard, as near as we can tell. Okay, so just as an example of a Hamiltonian path, a gray code is a Hamiltonian circuit of the unit cube. So I drew the 3 cube here, and I labeled all the corners. So here's 0, 0, 0. Here's you go out the x-axis, there's 0, 1, 0. You go out the y-axis, there's 0, 0, 1, 0, 1, 0. And where's the z-axis? There it is, 1, 0, 0. Sort of stuff. A gray code is when you make a Hamiltonian circuit of the n cube. So the idea is that you're starting at the origin and you're going out to 1, 1, 1 in such a way that you visit every vertex. And you can do the simplest thing here. So let's see, what's the simplest thing? How about going over, 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 and then up, over, and over? Okay, and now it lists all the binary numbers between 0 and 2 to the n minus 1 in an order that happens to change only one bit at a time. So for example, in going from 0, 0, 1 to 0, 1, 1, you only change the second of the 3 bits. That's convenient when you're building a device because you might want to have that for example, you're recording 3 bits, and so there's 3 wires, and they're running across the recording device, and you don't want to have that one of the wires disconnected from the recording device, but the other wire is still connected, and so you end up with a spurious value that in this case would be what 1, 1, 0. Instead, you want that only one bit changes at a time, and the gray code exactly gives you that. Okay, another example, really going through a wide variety of graphs, just trying to make sure that everybody has the same vocabulary. The actual sort of understanding of graphs, we're sort of anticipating that a person has at least a basic understanding of graphs just from programming. Okay, so a weighted graph associates with each edge a real number weight, sometimes called a cost. And here's an example. I have the airline miles from San Francisco to Boston is 2704. The airline miles from San Francisco to Chicago is 1846. So with each edge, I have associated the number of airline miles. If, for example, you wanted to traverse this graph, you might want to do it in the way that covers the least number of miles. So many problems in practice are modeled with weighted graphs. Shortest path, given a start and an end node, find me the path of least cost. So if, for example, I asked to drive from here to Chicago in the minimum amount of time, I would label every city in the country with how much time it takes to travel it. Every edge in the country, every road, with how much time it takes to travel it. And then I would say, find me the minimal path from here to Chicago. And of course, we've seen that everybody knows that there's an efficient algorithm to find the shortest path, Dijkstra's algorithm. Oops, I spelled Dijkstra correctly, but I didn't put an S, I put an A on the end. Oops. Dijkstra's algorithm will find the shortest path, and you can see that finding that shortest path has really changed the world that we live in. The ability to find the shortest way to do a job makes the world a radically different place. The second example is a traveling salesman problem. And again, I imagine everybody has heard of the traveling salesman problem. You give me a start node, you might, for example, take the start node of Boston. And I'm going to find a circuit that visits every city in the country, might not cover every edge, visits every city in the country, and does so at least total cost, at minimal total cost. Okay, and that's the traveling salesman problem. And although the two problems seem very much alike, the shortest path and the traveling salesman problem both involve minimizing over graph edges here, nonetheless, we know the first is easy. Dijkstra's algorithm gives you a rapid solution. We've all used them all the time on our phones. We believe the traveling salesman problem is in fact inherently difficult. We can't prove that, but we believe it's true. Okay, so again, going through some different kinds of graphs, trying to make sure that everybody has the same background on the different graphs. We bring together all the different words that people may have heard. We've seen that graphs are about nodes and connections, not how they're drawn, but we can ask some questions about drawing the graph. So the most important question that you can ask, the definition of graph is planar, P-L-A-N-A-R, planar. It fits in the plane. If you can draw it in the plane so that its edges intersect only at their endpoints. And the most famous example of a graph that is not planar is the so-called gas, water, electricity graph. So you have the gas company, the water company, and the electricity company, and you have three houses, house 0, house 1, house 2. Can you run a line from each of the companies to each of the houses without the lines ever crossing? I mean, it's dangerous for the water line to cross the electricity, and of course, it's silly. But the point is that you can't. That at some point, you've gonna have to have that two of those edges cross. Just try it. Take out a pencil and try to draw a gas, water, and electricity company, and then draw a house near house 1 and house 2. And you start drawing, and you get to some point where the house 1 is entirely surrounded by edges. And in order to get from the electricity company to house 1, you've got to go through that entire surrounding of edges. Okay, so a graph is planar if it can be drawn on the plane so that its edges don't cross, or intersect only at their endpoints. But that's not possible for this graph. So there are lots and lots of, although the problem is not solvable in that sense, nonetheless, there's lots and lots of software that tries to do the best job that you possibly can. And an example is, the widely used example is the free software GraphViz, which is produced by AT&T. Gosh, it must be 15 years ago now. That does the best job. It uses a number of heuristics to try to do the best possible layout of a graph. Okay, and really ticking through just a number of topics that a person has seen, and one of the topics that a person may not have seen, one of the things that we're talking that a person may not have seen, is Euler's formula. If you give me a simple planar graph, then you have to have that the number of planar regions equals the number of edges minus the number of nodes plus 2. The number of planar regions equals the number of edges minus the number of nodes plus 2. Okay, so let's go through it. Here's a graph. Plainly, it's obviously drawn in the plane. Whoops, the sun came out at a bad time. Sun hasn't been out all day. Okay, so here, edges. Well, it's easy to count the edges. There's 4 of them. Vertices, it's easy to count the vertices. There's 4 of them. Planar regions, that's the only one with a bit of a trick to it. That's clearly a planar region, that triangle. But the area outside is also a planar region. And of course, you can just simply do the arithmetic. That R equals E minus V plus 2. R equals 4 minus 4 plus 2. Okay, so the outside is the only part that might give a person a little bit of trouble there. Now, the proof is done by induction on the number of edges, and for the base case, you just take any single edge, and then for the inductive step, you add in an edge. I'm not actually going to go through the proof, but for the inductive step, you add in an edge, and you have to do a little bit of manipulation that didn't seem completely relevant to what we're talking about. We're trying to bring vocabulary together, but nonetheless, the point is that for planar graphs, there's a simple relation that governs what can happen in a planar graph. Okay, last topic for the day. We talked about this last time also when I talked about the four colors suffice. A coloring of a simple graph is an assignment of colors to the nodes so that adjacent nodes have different colors. And here I took that graph that I've been using as kind of a random example throughout some of these slides, and I did a two coloring. There's red and there's blue. Never is it the case that a blue is connected to, never is it the case that a red is connected to red. However, you'll notice here that there is a blue connected to a blue. So never is it the case that a red is connected to a red. However, you'll notice that I did not successfully two-color this because I have a blue connected to a blue. Now, if you give me an additional color, if, for example, you took N1 and made it green, why now I'm golden, and now I have a three coloring. So the chromatic number of a graph is the smallest number of colors that suffice to make a coloring. The smallest number of colors that suffice to make a coloring. And clearly it suffices here to have three colors, red, blue, and green. The basic idea of colors is that those categorize what can happen. So, for example, if we try to lay out the graph of all the courses at St. Michael's, we're trying to figure out a schedule for courses. So we lay out the graph of all the courses at St. Michael's, and we color all of Jim Heffron's courses red. We color all of Mike Larson's courses blue, sort of stuff. And then we can't have two courses at the same time if they're both taught by Jim Heffron. So we can't, if we connect courses together when they taught at the same time, why we can't have two red nodes connected, you can't have two blue nodes connected, etc. So coloring is putting the nodes into different categories. It's not actually coloring, it's putting the nodes into different categories. And the question just simply is, what's the minimum number of categories you can get away with? Okay, very good. So as with the other video and what we're doing in chapter 10 here is we're just simply trying to make sure that folks have a vocabulary, have an understanding of what kind of the vocabulary is about. Okay, very good.